Students, now we will discuss the periodic properties of the elements, and here we are going to start about the atomic radius. I want to tell you, finding the size of atom is a lot more complicated than measuring the radius of ball. Why it is so? There are two reasons. The size of atom is very small and the electronic cloud surrounding the atom does not have the sharp boundary. So, the determination of the size cannot be precise. Therefore, an estimate of atomic size can be made by knowing the distance between the atoms in a combined state. So, let us discuss the definition of atomic radius. It is half the distance between the nuclei of two combined atoms. So, if we are discussing the covalent radius, the distance between the two atoms when they are bounded together by a single bond in a covalent molecule, it is half of the distance. Actually, it is the half of the distance between two atoms when they are bounded together by a single bond in a covalent molecule, that is called as the covalent radius. Bond distance in the chlorine molecule is 198 picometer and half of the distance is 99. So, the atomic radius of the chlorine is 99 picometer. So, what is the metallic radius then? It is half the internuclear distance separating the metal cores in a metallic crystal. For example, the distance between the two adjacent copper atom is 250 picometer, and hence the metallic radius of the copper is 128. Actually, what is the atomic radius? It is the half of the distance between the nuclei of two combined atoms. Then what is the van der Waals radius? It is the half distance between the two adjacent atoms when they are not bonded together by any bond, and it is greater than atomic radius. ये atomic radius से बड़ा होगा. So then what is the variation of atomic size in the period? So what happens to the atomic size in a period? Atomic size generally decreases across the period from left to right. It decreases from left to right. It is because within the period, the outer electrons are in the same valence shell and the effective nuclear charge increases as the atomic number increases, resulting in increased attraction of electrons to the nucleus. Let us see here. If we see lithium, it's 152, then beryllium it is 111, boron 88, carbon 77, nitrogen 74, oxygen here it is 66, and fluorine is here 64. So, the atomic radius decreases, that is due to increased attraction of electrons to the nucleus. Atomic radii of noble gases are not considered here. For noble gases, van der Waals radii is calculated. Variation of atomic size in a group. Within a group of periodic table, the atomic radius increases regularly with the atomic number. It is because down the group, principal quantum number increases and the valence electrons are away from the nucleus, and also inner energy shield the outer electrons from pull of the nucleus. So, the effective nuclear charge decreases and hence the atomic size increases. So, we can say that the number of shells increases as we move down the group, and also there is a you can say decrease of effective nuclear charge. So, the atomic size or the atomic radii increases. See here, lithium 152, sodium 186, potassium 231, rubidium 244, and cesium is 262. So, there is a regular increase of atomic radius as we move down the group. What is the ionic radius? Ionic radius is the distance from the nucleus of an ion up to which it has its influence on its electron cloud. Cation is formed by removal of electron, so it carries positive charge. Anion is formed by gain of electron, so it carries negative charge. The ionic radii can be estimated by measuring the distance between the cations and anions in the ionic crystal. In general, the ionic radii of element exhibit same trend in the atomic radius. What about the size of cation? A cation is smaller than the parent atom because it has fewer electrons while its nuclear charge remains same. So, effective nuclear charge increases. Cation is formed by loss of electron. The number of electron decreases in the cation, so there is increase in effective nuclear charge. For example, the atomic radii of the sodium is 186 picometer as compared to ionic radii of sodium positive ion, which is 95. What about the size of an ion? The size of an ion will be larger than that of the parent atom because the addition of one or more electron would result in increased repulsion among the electrons and decrease in the effective nuclear charge. For example, ionic radii of chloride ion is 181 picometer, whereas the atomic radii of chlorine is 99 picometer. So, it is the reverse of the size of cation. So, what are the isoelectronic species? The species which carry same number of electrons are called as the isoelectronic species. The species like atom or ion which carries same number of electrons are called as the isoelectronic species. For example, here you see aluminum 3 positive ion, magnesium 2 positive ion, sodium 1 positive ion, neon, fluoride ion, oxide ion and nitride ion all carries 10 electrons. So, these are the isoelectronic species. The next one is ionization energy or the ionization enthalpy. This is the amount of energy required to eject most loosely bound electron from outermost shell of a gaseous atom is called as the ionization energy. For example, if we eject the electron from the sodium atom and sodium ion is formed, the amount of energy which is required to eject the electron is called as the ionization energy. Then what is the successive ionization energy? In successive ionization energy, the amount of energies required to eject the outermost electron from the outermost electron. Successive ionization energy, the energies required to eject the electron from outermost shell of a gaseous atom in a succession, one after another, is called as successive ionization energy. For example, in case of magnesium, there are 2 electrons. We first eject 1 electron and magnesium positive ion is formed, and then we start ejecting the second electron to form magnesium 2 positive ion. The first ionization energy is called IE1, and in removal of second electron there is a second ionization energy IE2. So, what are the factors affecting the ionization energy? First is atomic size. Larger the size, it is easy to remove the electron, so ionization energy is low. If size is large, definitely electron will be easily ejected and hence there will be low ionization energy. Second is the effective nuclear charge. More the effective nuclear charge, more difficult to remove the electron, and high is the ionization energy. If the effective charge is more, So it is very difficult to eject the electron and the ionization energy will be higher. Shielding effect. More the shielding effect of nuclear charge by the inner electron, less the effective nuclear charge, so there is a low ionization energy. If the shielding is more by the inner electron, effective charge will be less, size will be increased and ionization energy will be decreased. Then is the stability of half-filled and fully filled orbitals. Removal of electron is more difficult from elements having stable half-filled and fully filled electronic configuration. So the ionization energy is high because it is difficult to eject the electron from half-filled and fully filled stable configuration. And the fifth one is penetrating effect. The s electrons are more close to the nucleus as compared to the p and d electrons. So we can say that s electrons are more penetrating towards the nucleus, so removal is more difficult from s electron as compared to p and d electrons. Then what is the variation of ionization energy across period? Effective nuclear charge increases and the size decreases. So if the size will decrease, definitely the outermost electron will be tightly held by the nucleus and hence the ionization energy will be more. So as we move left to right in the periodic table, ionization energy is increased. As we go down the group, number of shells increases, so the atomic size increases, shielding of nuclear charge by the electron in inner level is also increased, so effective nuclear charge decreases. So there is a removal of outermost shell requires less energy and hence we can say the ionization energy decreases. In simple words, we can say that as we move down the group, the number of shells increases, the atomic size increases. Due to this, the ionization energy also decreases. Let us see the variation of ionization energy. So noble gases which have closed electron shells are very stable and electronic configuration have high ionization energy in the period. So noble gases are having outermost stable configuration. So due to that, it is very difficult to eject the electron. So their ionization energy is very high. Reason is stable outermost electronic configuration. Low ionization energy of alkali metals can be correlated with their high reactivity. We can say that the alkali metals are having only one electron in their outermost shell. Due to this, it is very easy to eject the electron. So their ionization energy is very less. Fast ionization energy increases as we go left to right in the periodic table and decreases on moving down the group. From these graphs, you can understand the variation of the ionization energy along the group, and in case of the first period, we have taken lithium, beryllium, boron, nitrogen, oxygen, fluorine and neon. There is a regular increase in ionization energy. We have also taken this graph of alkali metals where there is a regular decrease as we move from lithium to cesium. Variation in this variation of ionization energy, we are having certain assumptions. First, ionization energy of boron is slightly less than that of beryllium, even though the boron has greater nuclear charge. Why it is so? The reason is electronic configuration. In case of the beryllium, configuration is 1s2 2s2. In case of the boron, configuration is 1s2 2s2 2p1. S orbital is attracted to the nucleus more than p electron. So penetration of 2s electron to the nucleus is more than that of 2p electron. Hence what happens? The 2p electron of boron is more shielded from the nucleus by the inner core of the electrons than the 2s electrons of beryllium. Therefore, it is easier to remove 2p electron from the boron as compared to the removal of 2s electron from the beryllium. So, we can say that boron has smaller first ionization energy than beryllium. Similar type of exception is also there in first ionization energy of oxygen. So, that is less than that of nitrogen. In this we can say that electronic configuration. See here, nitrogen has configuration 1s2, 2s2, 2p3 and oxygen has 1s2, 2s2 and 2p4. 2p3 is having half field stability. Due to that, it is difficult to eject the electron from nitrogen as compared to oxygen. So, nitrogen has stable half filled 2p orbital, while oxygen 2 electrons are present in one of the 2p orbital. So, consequently, it is easier to remove the fourth electron of 2p from the oxygen easily, because the nitrogen is having the half filled stability. So, hence we can say here that first ionization energy of oxygen is less than that of nitrogen. First ionization energy values of third period elements sodium, magnesium, silicon are 496, 737 and 786 kilojoule per mole respectively. Predict whether the first ionization energy value for aluminum will be more close to 575 or 760 kilojoule mole per mole. Justify your answer. Here we have taken the elements. Sodium is having configuration, outermost configuration 3s1, magnesium 3s2, aluminum 3s2, 3p1 and silicon 3s2, 3p2. It is more close to 575 kilojoule per mole. The value of aluminum should be lower than that of magnesium, because effective shielding of 3p electrons from nucleus by 3s electrons. This is all about the ionization energy. So, now in next video we will discuss rest part of this chapter. You solve this assignment, and till that, goodbye and have a good day. Bye.